Hello everyone, and welcome to today's webinar, Smart Chart webinar series focused on AFM and OP. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Sarah Ostrowski, Surface Properties Manager at EAG Laboratories.
Good morning, good afternoon, or good evening, everybody. And thanks for taking the time out of your day to tune into our Smart Chart webinar series. Today, we'll be covering atomic force microscopy and optical profilometry, which is also known as white light interferometry. I'm Sarah Ostrowski, manager of the Surface Properties Group at EAG's lab in Sunnyvale, California. My group includes a variety of techniques, including AFM, OP, XRF, TXRF, and nanomechanical testing. Over the last 15 years, my career has been focused on surface analysis and materials characterization with a particular focus on AFM, OP, and TOF sims. This webinar will cover two techniques often used to characterize surface topography and roughness, AFM and OP. My goal is to emphasize the usefulness of these techniques by showing you data from real-world examples. The webinar will be divided into 4 general sections. First, I'll give a brief introduction to EAG and to our Smart Chart, which is the inspiration behind this seminar series. In the second portion of the webinar, we'll delve into AFM, the operational theory of basic topography, AFM, and several advanced AFM modes, including material property mapping, scanning capacitance to measure dopant distribution, and conductive AFM. We'll review several representative examples for each of these analysis modes. The third section of the presentation will focus on OP, how it works, and some interesting applications. Finally, I'll discuss complementary techniques and summarize everything we covered today. EAG has several hundred highly educated and experienced employees working in labs around the world. EAG offers 40 analytical techniques with AFM and OP at our Sunnyvale, California, and Netherlands locations. Our range of equipment and diversity of expertise allows us to provide our clients with a comprehensive, peer-reviewed report within a few days of sample receipt. And when necessary, we can even provide same-day service. Our company was established in 1978, so we've been around over 40 years, bringing lots of experience to the table. This chart is the spectroscopy and microscopy analysis resolution tool, which we used to call the bubble chart. Each of the bubbles represents a different analysis technique, and the bubble size indicates detection range and analysis spot size. The surface chemical analysis techniques are inside of the box. Outside of the box, on the right, are the bulk techniques. These techniques have a range of detection limits, but don't provide information regarding depth. Below the box are the imaging techniques. These can measure surface properties and features of various sizes, but they don't inherently provide chemical compositional information. Another feature in the chart is color. The bubbles are color-coded to indicate the type of information each technique provides. Looking inside the box of surface analysis techniques, the blue bubbles show techniques that provide atomic composition, and the red bubbles provide molecular bonding or oxidation state information. Green bubbles provide imaging information. Today, we'll be covering 2 of the imaging techniques, AFM and OP. In this first section of the webinar, we will discuss AFM, which is also sometimes called scanning probe microscopy. Of the two techniques we are covering today, AFM images the smaller sized areas. The most common application of AFM is to characterize surface topography and roughness with very high resolution. So why is roughness important? The first thing that comes to mind is purely cosmetic. Topography can dictate whether a surface is visually and tactilely appealing, which is critical for many commercial products. Surface topography can influence the functionality and performance of a material too. It can reveal inhomogeneities in films. It can affect how well bone can grow into dental implants. And topography can even affect how a surface responds to water. For example, water beating up on a flower petal, which happens partially because of its microstructure imparting super hydrophobic properties. Although AFM is most often thought of for its use in topography, it can provide much more. It can map various physical, electrical, and magnetic properties too. We'll get into more details about these advanced modes later in the presentation. At our Sunnyvale facility, we have two Bruker Dimension Icon AFMs. These instruments have versatile sample handling capabilities, so we can fit very large samples, even 300 millimeter wafers. The scan sizes can range from submicron up to 90 micron by 90 micron, and the scanner can track height variations of up to 10 microns. I'd like to take a moment to point out various components on the instrument. Here is the 200 millimeter sample stage with in situ optics on the left side. Directly above the stage is the scanner, which houses the piezoelectric scanner tube and laser assembly. The AFM probe mounts on the underneath of the scanner, and the inset shows an SDM of a typical AFM probe. The diving board structure is called the cantilever, and the triangle extending beneath it is the tip. These probes are commonly made of either silicon or silicon nitride and are usually manufactured using a photolithography process to have very specific geometries and tip radii down to several nanometers. We have a wide variety of probe types in stock, so we're ready to address a variety of sample types and applications. Our instruments have accessories allowing for a broad range of AFM-based measurements, and we'll discuss a lot of these today. Of course, there's basic topography imaging, and we do have a fluid cell, which enables analysis of topography and mechanical properties of materials under solution. The AFMs can be used to map various mechanical properties, electrical and magnetic properties as well. We've done all of these modes commercially and are happy to work with you on developing the appropriate method to solve your analytical challenges. The most basic operational mode for AFM is known as contact mode. This mode is also the basis for many of the electrical techniques. The schematic on the left shows the main components of the analysis. There's a probe attached to a piezoelectric tube scanner, which allows for fine control of the probe movement. There's a laser, a position-sensitive photodiode, and feedback electronics. In contact mode, the tip is raster scanned back and forth in direct contact with the surface, while a laser light is reflected off of the back side of the cantilever onto the detector. When the tip encounters a point along the surface at a new height, the position of the light on the detector changes. Feedback electronics are used to maintain a constant position on the detector by adjusting the cantilever height with a voltage applied to the piezoelectric tube. The voltage is converted to height in the instrument software. Tapping mode is the other basic operational mode in AFM. It uses the same instrument components as shown in the previous slide, but in this case, the probe is not in constant contact with the surface. Instead, the cantilever is oscillated near its resonant frequency. When the tip encounters a height change, the amplitude of the oscillation will change as well. This amplitude is the parameter that is controlled, or in other words, held constant by the feedback electronics. The voltage used to maintain constant oscillation amplitude is converted to height units in the software. Tapping mode is the more common way to measure basic surface topography because it's gentler and can provide better lateral resolution. So now that we've discussed the basic operational principles of AFM, let's talk a little bit about the data output. Here is an example of an AFM image. It's a 5 micron by 5 micron view of a mosquito wing. AFM images are false colored and a variety of color scales can be used. This yellow-brown scale is pretty typical for the AFM community. On this scale, the brighter yellow pixels are taller heights and the darker pixels are lower heights. AFM images contain a wealth of information. They're not just pretty pictures. The enlarged view on the right helps show this pixelation. There are around 260,000 pixels in a standard square AFM image. Each pixel in an image contains a height value that can be used to quantify surface roughness mathematically with a series of roughness statistics. Roughness statistics are a great way to quantitatively compare samples. Also, a lot of our clients will have certain industry-driven roughness specifications that they're trying to meet. There are a large number of different roughness parameters. Two of the more common ones are average roughness and root mean square roughness. This is a line profile of a surface where the lowercase h's are the difference in height between the surface and the mean plane. Average roughness is the average of the height deviations of each point on the surface relative to a reference plane. RMS is the square root of the mean squared height. You may come across parameters denoted as R or S. R and S parameters are still used somewhat interchangeably in the metrology community, but technically R parameters refer to one dimensions, so for example from a line profile, and S parameters refer to two dimensions or from the full image. Another common parameter not explicitly shown here is Rmax or SZ. This is simply the difference between the tallest peak and the lowest valley. Now that we've reviewed the basic principles of AFM, I'd like to share a few examples of topography analyses, including thin films, silicon wafers, and a hard drive disk. Next, we'll discuss a few advanced AFM applications, such as material property mapping of a copolymer, scanning capacitance of a transistor, current mapping on a perovskite material, and Kelvin probe microscopy. This first example highlights how roughness can be used to quantitatively compare surface quality. This image is of a thin copper film as received. It has an average roughness of 12 nanometers. If you tuned into Monica Newberger's presentation 2 weeks ago, you'll already be familiar with X-ray photoelectron spectroscopy, which is used for chemical analysis. XPS instruments can also be used for depth profiling, in which an argon ion beam is used to gradually etch away, or sputter, the surface to study chemistry as a function of depth. So how does this sputtering affect the surface roughness? This next image shows the same film after removing 500 nanometers of material with an argon beam in an XPS instrument. Notice that the Z-scale is now much bigger compared to the as-received sample, and the RA is much higher, and the topography is also drastically different. Roughening like this can negatively impact depth resolution and data quality in XPS depth profiles. Of course, EAG knows that DC sputtering has this effect, which is why we use something called Zala rotation for our XPS measurements. Zala rotation involves spinning the sample during the sputtering process to minimize roughening. The third image is of the copper film after the same amount of sputtering, but while using Zala rotation. You can see that the topographical appearance and roughness is virtually identical before and after. Height parameters like RA are important to characterize topography, but sometimes they don't tell the whole story about a surface. In this example, there are two silicon wafers that were cleaned by different methods. These are 2 micron by 2 micron images, which is a typical image size for a very smooth sample. And a good rule of thumb is that if you can see your reflection in the surface, it's probably considered to be smooth. You can see that the wafers have very similar average roughness values, but their textures are far from the same. The image on the left has randomly arranged points sticking up, and the wafer on the right shows a texture with strong directionality. This example highlights how the images, and not just the numbers, are helpful in understanding surface topography. It's beyond the scope of this webinar, but there are a series of spatial statistics which can measure the degree of isotropy in surface texture. The value for that parameter is in fact quite different for these two samples. Along with roughness, topography data can be used to measure critical dimensions. This example shows measurements of a structure at the landing zone on a hard drive disk. Believe it or not, the hard drive industry used to be a really big customer for EAG in the past. The photo in the upper left shows the hard drive platter, and the image below it is the landing zone, which controls friction by reducing the contact area between the hard drive head and disk while it's at rest. The donut-shaped structures are our focus here. The AFM image is quite large, about 77 microns by 77 microns, which is near the largest scan size possible by this technique. Keep this in mind for our discussion later on OP. AFM software has many tools for digging deep into data sets. In this case, a line is manually drawn through the center of the structure, and the output is a graph called the line profile, which is height versus lateral distance. It's possible to measure the width and the depth of the structure from the profile. Beyond basic topography, AFM instruments can map various mechanical properties. If you're familiar with AFM already, you may have heard of phase imaging, which was the original way to map mechanical properties. Phase imaging certainly did provide useful data and is still around, but the phase images were just a combination of several mechanical properties all lumped together. Bruker has developed a new operation mode that can actually image each mechanical property individually, and they call it peak force quantitative nanomechanical mapping, which is quite a mouthful. So I like to say peak force Q&M, or just Q&M for short. From a customer's perspective, peak force Q&M is more semi-quantitative than quantitative though. So let's go over how this works. Peak force Q&M is similar to tapping mode, except that the probe is oscillated at a frequency much below the resonant frequency. That slower tap enables a force curve to be extracted at every pixel in the image. A force curve is force versus tip sample distance. An example is shown here. And it's measured as the tip approaches and then retracts from the surface. 260,000 full force curves would be a lot of data though, and computers aren't quite at the point to handle that. So instead of saving the entire force curve, the software just calculates 4 values from it and throws the rest of the data away. Those 4 values are modulus, adhesion, deformation, and dissipation. The peak force Q&M example is a reference sample of a two-component polymer system, polystyrene and low-density polyethylene. The copolymers are spin cast onto a silicon substrate, creating a film with varying material properties. In this height image here, you can see the perimeters of various circular regions that are probably related to polymer domains. But which region correlates with which polymer? That question can be answered from the material property maps. There's not much contrast in the adhesion image, but there's great contrast in the modulus and deformation images. The mid-sized circles have lower modulus and correspondingly higher deformation. We know that polystyrene has a modulus around 2 gigapascal, while the low-density polyethylene modulus is around 0.1 gigapascal. Therefore, the mid-sized circles must be low-density polyethylene. I think it's interesting that the QNEM can detect polystyrene domains within the low-density polyethylene, like right there, which emphasizes how high lateral resolution material property mapping can be informative. In practice, QNEM is not great for absolute quantification, though. There are numerous issues with the mathematical models used for the calculations. The modeling issues are generally related to the actual physics and geometry of the AFM measurement. So for absolute quantification of nanomechanical properties, we generally recommend standalone nanoindentation. Nanoindentation can also provide maps, but at lower lateral resolution. Of course, EAG also has many other techniques to characterize chemical properties of polymers, such as FTIR and TOF-SIMS. It's possible to use AFM to map various electrical properties with specialized sensors and metal probes. The probes for electrical AFM techniques can be metal-coated or solid metal. Either way, they generally have a somewhat larger radius than the probes used for topography, say around 25 nanometers instead of 5 nanometers. In today's webinar, I'll be covering scanning capacitance, conductive AFM, and Kelvin probe force microscopy. Scanning capacitance is a way to map the distribution of electrically active carriers in semiconductors with high lateral resolution. So, if your structures are too small to be tested by SIMS, scanning capacitance may be the way to go. Scanning capacitance is operated in contact mode, and in essence forms a metal oxide semiconductor capacitor with the sample. That oxide being the native oxide or purposefully grown oxide. During the measurement, an AC bias is applied to the sample, which causes the accumulation and depletion of carriers. The resulting capacitance variations are detected with a capacitance sensor. I'd like to note that the output is DC over dV, so you're not directly measuring capacitance by this technique. Along with the electrical information, height data is also collected in SCM mode. As an example of SCM, I have data from the gate area of a commercially available power MOSFET. SCM can be performed top-down or in cross-section. My colleagues at EAG have extensive experience in sample preparation of devices just like these. We've been given fully packaged samples in the past and performed the depackaging, stripping, cross-section, polishing, what have you, all in-house. In this case, we have a top-down optical view of the MOSFET with a dotted red line showing the plane where that was cross-sectioned. On the right are optical and SEM views of the target area. The SEM data was captured at approximately the regions shown in the orange box. On the right is the corresponding height image. You could see the metal and poly layers near the top of the image, but not much else. The dopant distribution is evident from the scanning capacitance images. Here we have the DC over dV amplitude image, which maps relative dopant levels. In this case, brighter colors indicate lower doping. On the right is the DC over dV phase image, which shows dopant type. Yellow in this case is P, and dark brown is N. The speckled color corresponds to no signal. P wells and thin N wells are detected in an N substrate, and those squiggly extensions coming out the bottom are epistacks. Finally, this is the SCM data image, which combines the data in the amplitude and phase images. This type of data is not typically shown on the yellow-brown color table. In this case, the pink to purple colors indicate high to low P doping, and the orange to yellow indicates high to low N doping. This is just a smaller area, higher resolution view of that same sample. The thin end well structures are more clearly observable on this scale. Of course, we know this is an older technology, but it was a publicly available device that we could take apart, collect data from, and show externally. But we can do SCM on much smaller structures than this. Another type of electrical AFM is conductive AFM or tunneling AFM. These techniques both provide maps of current variations ranging from femtoamp to microamp levels. From an operator's perspective, at least on a Bruker icon tool, there's not a lot of difference between conductive AFM versus TUNA. It's just a matter of sliding a switch on an amplifier box and nothing more. My best guess is that some scientist was having fun with acronyms one day and thought they were very funny, and somehow that name TUNA stuck. At any rate, for both modes, a metal probe is used in either contact mode or peak force tapping mode. A bias is applied to the sample, and the current passing between the tip and sample is detected with a current amplifier. And of course, height data is also collected in during this process. The conductive AFM example I have to share with you involves perovskite, which is an organometallic halide material used in solar cells and light-emitting diodes, or LEDs. Perovskites have great promise as a new lighting technology because of their low cost, strong light emission, and tunability. Also, since they don't require high temperatures for processing, they can be used on a great variety of flexible or rigid substrates. And I get real excited thinking about cool light up clothes that we might have in the future. A general schematic of a perovskite-based LED is shown above. So this consists of two electrodes, hole and electron transport layers, and the perovskite active layers in the center. Light is emitted from the device upon activation with a voltage applied to the leads, and the color of the emitted light is determined by the energy band gap of the semiconductor. We recently collaborated with a summer intern from the University of Santa Cruz on developing perovskite LED materials. This was a large project that used several analytical techniques, but unfortunately going into the full details is beyond the scope of this webinar. Just know that we use TEM EDS to analyze the composition of the layers, and then XRD to characterize the crystal structure. One of the issues was that some of the students' devices weren't turning on. So to answer or to dig into that conundrum, we used SEM and conductive AFM. My colleague, John Mosquito, will be giving a webinar on SEM tomorrow. So if you're interested in the details on SEM, please tune in. But just short and simple, this technique images samples with higher lateral resolution than is possible by optical methods. These are images generated at EAG of the student samples. The elongated structures were unexpected and considered a possible culprit in the device failure. So she was interested in exploring their electrical properties, and we worked together to do TUNA experiments on her samples. On the top left is a 5 micron by 5 micron height image of a similar perovskite surface, and the elongated structures sitting on top of the surface are evident. On the right is a current map produced when a 500 millivolt DC bias was applied to the sample. In this case, bright colors indicate a high positive current reading. So the image shows that the elongated structures are not conductive. Line profiles through the images further exemplify this fact. So in this graph, the current signal is plotted in orange and on the left side, and the height data is on the right side and on the blue trace. You can see that the presence of the long structures with these X's coincides with the absence of current. The last electrical mode that I'll cover today is called Kelvin probe force microscopy and is also known as surface potential microscopy. This technique provides images of surface potential variations across an area as well as the typical AFM height image. KPFM works in what is known as lift mode. The AFM first images the surface topography in either tapping mode or peak force tapping mode. Next, the probe is lifted a set height designated by the user from the surface, and it rescans the surface at a constant height. So in other words, it uses the height information it generated in the first pass to maintain a set height, somewhere around a ballpark of 100 nanometers, for example. So during that second pass, an AC bias is applied to the tip. When the tip is above a material with different surface potential, the AC bias causes it to vibrate. The feedback electronics apply a DC offset to the probe in order to null this vibration. The DC offset voltage is therefore related to the difference in work function between the tip material and the sample material. The Kelvin probe dataset shown here is from a Bruker reference standard of patterned aluminum and gold. So it's more or less just a proof of concept showing that the technique can differentiate between materials having different work functions. The small blue rectangle in this optical image shows about where the Kelvin probe data was taken from. The height image clearly shows the interface between the two metals, and the contrast in the potential image shows that the gold has a higher work function as expected. We can look at this a little more quantitatively with a line profile through the potential map, which shows the measured work difference between aluminum and gold is 770 millivolts. This is close to the theoretical difference of somewhere between 800 millivolts and a volt. Most elements have a range of possible work functions because the actual work function depends on the material's specific crystal structure and other factors. Kelvin probe is great at measuring the surface potential difference within an imaged area, but in practice, we don't recommend it for comparing surface potential between samples. So to summarize this section, AFM provides quantitative topography and roughness information from surface regions smaller than 90 micron by 90 micron. It has sub-angstrom vertical resolution and very high lateral resolution. So I'm not being very specific about the lateral resolution because it's affected by several factors like tip size and shape, the image size, and the pixel density. The ultimate lateral resolution is limited by the tip geometry to a few nanometers. AFM can also image material, electrical, and magnetic properties by incorporating various sensors into the experiment. It is, of course, limited to smaller analysis sizes, and the property mapping is generally qualitative. Now we'll switch gears and review optical profilometry, which again is sometimes called different names like white light interferometry. Although we won't be covering it today, we also offer stylus profilometry as an alternative to OP. OP provides similar output to AFM, meaning topographic images and roughness statistics. OP images are from larger areas. The smallest area is 60 micron by 50 micron, which is around where the AFM leaves off. The largest image size by OP can be several tens of millimeters with stitching, which means that many individual 2 millimeter images are added together like a puzzle into a single composite image. A trade-off to the large imaging size is that OP doesn't have as fine of a lateral resolution as AFM. The lateral resolution is limited by the optics to be about 500 nanometers, but vertical resolution still approaches the ability of AFM in some cases. Selecting the right technique, AFM or OP, doesn't have to be a burden on you. We are happy to have discussions with you about your specific application to help you choose the technique most suitable for what you need. In California, we have a Bruker Contour GTX-8 instrument. Like our AFM, this tool has versatile sample handling capabilities. It can fit 300 millimeter wafers or samples up to 100 millimeters tall. Our lab in the Netherlands has a Bruker NP Flex system, and that can fit really odd-sized samples. Since this technique uses visible light, it's non-contact and non-destructive. The principle behind OP is that the surface height is detected by a light interference pattern. This interference pattern is created when a beam of light is split equally between the sample and a reference mirror. The light reflected off the surfaces is recombined and directed towards the detector. When the path length to the sample equals the path length to the mirror, an interference pattern is observed. The detector measures various aspects of the interference pattern, depending on the imaging mode, in order to determine height values. So there are two modes of operation for interferometry, and we'll go over both of them, PSI and VSI. Phase shifting interferometry involves having the reference mirror move in small increments of a fraction of a wavelength using a piezoelectric scanner tube. The mirror movement causes 90-degree phase shifts between the sample wavefront and the reference mirror wavefront. The intensity at each of the 4 phase shifts is monitored. Then, by mathematically combining the information from each phase shift, the software calculates the height at each point in the image. Because this mode involves mirror movements of a fraction of a wavelength, it can only be successfully used for samples with height variations of less than a quarter of a wavelength, so something around 150 nanometers. Smooth samples are also best characterized by this mode because it has the better height resolution of sub-angstrom. Representative applications that you use for PSI mode include silicon wafer and thin film roughness analysis. The other main operation mode for OP is vertical scanning interferometry, or VSI. In this case, the entire objective is moved vertically up to 10 millimeters. When a surface is at the focal point, the path length to the reference mirror equals the path length to the sample, and this corresponds to the maximum contrast in the interference pattern, or where the fringes are the brightest. The height of the objective at this position relates to the height at each point in the image. This animation shows the objective being scanned vertically and detecting the maximum fringe contrast at the focal points for each slice of the step structure. VSI mode is used for surfaces having height variations of greater than 150 nanometers, and its height resolution is about 6 nanometers. Now that we've discussed the principles behind OP, I'd like to share a few representative examples, including roughness on rough versus smooth samples, critical dimension measurements on that same hard drive platter we looked at in the AFM section, and automated dimension measurements of solder bumps on a ball grid array. This is a rough pattern metal part. On the far left is an optical image of the sample with the analyzed region shown in the green rectangle. OP images are by default displayed on a different color table than AFM. This color table is a rainbow gradient. with red being tall structures and blue being lower surfaces. Like AFM output, OP images are displayed in 2 dimensions and 3 dimensions. It's possible to calculate the same roughness statistics and also generate line profiles to measure critical dimensions. Here we show that the height of the weave is about 64 microns. I'd like to point out the imaging scale, which is 3 millimeter by 2 millimeter, which was generated by stitching together a few smaller images. This size image would not be possible by AFM. The Z-scale also far exceeds what's possible with AFM. The height variations, as you can see, greatly exceed that 150 nanometer cutoff for VSI versus PSI, so this data was collecting using VSI mode. This second example is of a polished silicon wafer. In contrast to the previous example, which had an RA of 22 microns, this sample is extremely smooth with a sub-nanometer RA. Obviously, this application falls in the PSI mode realm. I also want to point out that the image size is smaller. It's the smallest that we can achieve with the objectives on our instrument. The line profile shows the richness of the data content and could be used to extract one-dimensional roughness statistics. Our third OP example references back to the AFM section and the hard drive platter. With OP, we can actually examine much more than just a single landing zone structure. By stitching images, the entire hard drive platter was imaged. This image shows the long-range bow and shape of the platter. The small green rectangle indicates the portion of the platter where the landing zone is located. OP could image the full array of landing zone structures, which could be useful for identifying any anomalies in that array. And below is a line profile surveying the depths and widths of several structures. The array size is also much larger than could be achieved by an AFM scan. Using our highest magnification, it was possible to image a single landing zone structure at a similar size to the AFM data. This OP data provides similar critical dimension measurements and topography details such as the dimpling within the structure. While the resolution of the OP image is much less than AFM, this technique may provide sufficient information for the application. The trade-off is analysis time. OP is a heck of a lot faster, and therefore the service is more affordable. One last cool feature I'd like to share is the software's ability for high throughput critical dimension measurements. This example is of solder bumps on a ball grid array. The photo shows the particular device in question with a dime for size reference. And here are 2D and 3D images of the array. You can see this is about a 40 millimeter by 40 millimeter image, so quite large compared to anything possible by AFM. The bump heights were of critical importance for this application because height consistency, also known as coplanarity, improves electrical contact and signal yields while minimizing the potential for shorts. In other words, we want all these bumps to have the same height within, say, tens of microns. Of course, we could have a lab technician spend an obscene amount of time manually measuring the height of each bump using line profiles, as shown here. But with modern computing, this luckily is not necessary. The OP software has a feature called multi-region analysis, which is a pattern recognition algorithm that can identify regions of interest based on their height or spacing. In this example, multi-region analysis identified all 1,292 bumps in the array. This is an abbreviated version of the output table showing only the first 8 bumps. The details of the output table aren't important for the purpose of this talk, but just note that the area, diameter, height, and position of the bumps was recorded. With the positional information, it was possible to locate the bumps having the largest height deviations. In summary, OP is a fast, non-destructive method to characterize surface topography and roughness. It measures much larger areas than is possible by AFM, but with reduced resolution. This software has automation capabilities and pattern recognition post-analysis tools. The challenges that go along with the strengths are that there can be missing data in some cases from rough or angled surfaces. And another limitation is that thin, transparent coatings can confuse the instrument. It'll detect the topmost surface and the substrate. What possible workaround if that's a problem is that we can metal coat the sample, and that's something we can do at our facilities. Although I've alluded to it already, I want to explicitly show that OP and AFM are complementary techniques. They can be used in conjunction to provide the most complete picture of the surface texture. This data is from a solar cell. The AFM images at the top show the micro roughness and texture at a very fine scale. The solar cell also has waviness, or long-range shape and structure, which would never have been captured on an AFM scale. The OP images also nicely reveal this waviness and some sporadic pitting, so it's also useful as a survey tool. The webinar today only discussed AFM and OP, but there are other techniques for characterizing roughness, mechanical, and electrical properties. XRR, for example, is a technique available at EAG that can indirectly measure roughness. My colleague Ian gave a presentation covering XRR last week, and if you missed it and are interested, we can provide a link. SEM is an imaging technique that can provide morphology information and lateral critical dimensions. Tomorrow, actually, we'll be offering an SEM webinar at 11 o'clock Pacific time. And finally, several other techniques are complementary to scanning capacitance microscopy, such as DHEM, or differential Hall effect metrology, and dynamic SIMS. These both can characterize dopants. We'll continue the Smart Chart webinar series over the next few weeks to explore more of these techniques. I'll post the upcoming schedule after the next slide. But first, I wanted to take a moment to advertise EAG and why you should choose us to help solve your analytical challenges. We take client confidentiality very seriously, and we even do regular businesses with export control and ITAR companies. EAG has been around for 40 years, so we have very experienced experts and streamlined processes in place to make your project go smoothly. Many of our techniques are even actually ISO 17025 accredited. Our company offers over 60 analytical techniques, so one way or another, we can find you an answer. And I also want to mention that all of our locations are open during the shutdown, and we are accepting jobs. In some cases, there may be limitations on customer visits, or we may be operating at a reduced capacity, but we'll do our best to meet your needs within our lab network.